Right, so this morning we're going to have 4 talks. First, I'm going to give some guidelines on choosing a quantum Monte Carlo project, trying to give some additional things to think about and consider when picking problems that are hopefully a slightly different take from what we've heard already from the sort of technical side of how one does quantum Monte Carlo calculations. Then Nick Romero is going to give a talk about how one can obtain computational resources. And then after a break, we're going to have a talk on forces and also on non-adiabatic calculations. And then, then we'll have lunch, and in the afternoon, it's free for interactions with the instructors. So please talk with us, discuss projects that you have in mind or any other questions you have about the method. Right now is really the time to talk through those issues. Okay, so let's begin. So what I want to do is give some guidelines, and then I'm going to talk through some examples which we've been seeing throughout the week, what might make a project particularly easier or harder in terms of the quantum Monte Carlo. So what I'm going to do, basically I thought up 12 additional points to consider when picking a quantum Monte Carlo project. And then I'm going to talk about some examples of recent projects and basically my views of what makes those perhaps easier or harder for the Monte Carlo. And I'd like to stress that this is not what makes them stronger or weaker in terms of science, but what's going to make them easier or harder in terms of doing the Monte Carlo. Now, of course, I have to give a few disclaimers here. So, of course, many of the considerations are common to other computational sciences, and a few of the points would certainly apply if you're doing a density functional or quantum chemical investigation, or even a model study. And of course, I'm only listing 12 points, and these are the ones that occurred to me first, and of course there are many more. If you asked David today, he would have a list of some other points. Hopefully there'll be some overlap, but it wouldn't be complete overlap, of that I'm certain. And the same goes for Luke Schulenberger, Miguel Morales, and everyone we've been hearing from. So for the points I'm making, I need to make a distinction from what we've been hearing earlier in the week, right? So these are more opinions, which can be a point of discussion, so they're not mathematically proven facts or rules. And of course, we always have to bear in mind that sometimes, a breakthrough paper is going to ignore all the standard considerations, right? But if you're breaking normal considerations, it's usually good to know that you're doing that, right? And so you're taking on a risk when you do that. All right, so point 1, these are not in a particular strong order. So when picking a project, obviously you want to consider, what's the audience for this paper? What's the audience for this work? So obviously we want to try and structure the investigation so that the greatest number of people are going to be interested. And we want to make our results relevant to others. So we want to get beyond just reporting a number and get to some understanding which is going to have some longer term ramifications, like more people will be interested. So the reason I mention this is it's very easy to get caught up in obtaining just one more digit of accuracy. And of course we have a particular focus on accuracy and the methods that we've been discussing here. But if you really do want one more digit in accuracy, you better make sure that digit is really warranted, and there's a quote unquote a customer or some experimentalist who's going to be particularly interested in that, or there's an important problem that's going to be solved with that increase in accuracy. So are experimentalists going to be interested? Will the wider electronic structure community be interested? Because if your audience is just going to be quantum Monte Carlo people, that's a relatively small field. And so if one's going to do that work, one wants to understand where one is in the investigation. So of course to have greater impact, if you can get to the point where you can either prove or disprove a mechanism in a particular material, particular interaction, then that's going to be much more significant. So for example, if through more accurate calculations you could show that some interaction or some phenomena either is really dominating as a process or has no relevance whatsoever, then that could be much more significant, right? So then the model Hamiltonian people could drop that term, for example, Right? That would cross fields. Okay, point 2. And so this, of course, is a quantum Monte Carlo workshop, but we have to remember, just because you have a hammer, it does not mean everything is a nail, right? So not every project is going to be well suited to quantum Monte Carlo. There are limitations, not only cost, also accuracy, and the degree of complexity that can be studied today. So we need to consider whether QMC is really going to be a good choice. We might, of course, want to develop a way to address some difficulties, but nevertheless, there are limitations. And of course, the key thing here is when we're trying to make a prediction, there are many factors that determine the overall accuracy and hence utility of the investigation. So for example, suppose a problem has disorder, or there are many defect configurations to study, or there are lots of isomers to look at, or for example, we need to study a liquid, right? Then we're going to have to do some configuration sampling of some sort, right? And that's going to be harder. And in some cases, we can obtain statistics. In other cases, there may be too many. So there may be other methods that can compute more properties and get a better overall picture. Alternatively, it may be possible to learn something from the quantum Monte Carlo, which can then inform our choice of a simpler method. Right? That's what we want to do. And so another example of an error that would be hard would be if we do a particularly heavy element where relativistic effects start to be important. So there is some work looking at spin-orbit interaction, but that's not an everyday technique. And so if we ignore those relativistic effects, or they're important beyond what's folded into the pseudo potential, then of course we're solving the wrong Hamiltonian. So we can solve that very, very accurately, but that may not apply to the physical system. So that's something we have to be very careful about. And there are lots of examples here, so an easy one would be temperature effects to worry about. Yes?
The temperature effects, you could still use the QMC for the electronic part.
Yeah.
And then go back into something.
Right.
For
Right, so the comment was that we could, with temperature effects, we could still perhaps use quantum Monte Carlo for the mean field, for the electronic part, essentially. And of course, that's what we do very often. But there may come a point at which we can't apply a zero temperature theory for the electronic structure. And we're going to see some examples where one can consider that to be the case later today.
And maybe I would argue that it is easier to put the temperature effects into QMC.
So the comment was that it may be easier to put the temperature effects. And it may, there are ways of including temperature effects in the quantum Monte Carlo, but if this is significant, then just using a standard fixed node calculation is not going to be enough.
Right.
So, number 3. So this point is about making our life easier, should we choose to make it easier, right? So we can favor studies of systems where other methods have lots of difficulty over small improvements in accuracy. So if we're looking at a system where density functional theory is doing very well, and we're only trying to resolve a small percent change in an elastic constant, for example, then we're obviously going to have to work very hard and be very consistent in finite size extrapolation and in having high quality wave functions, for example, in order to be certain that we really are improving in accuracy. Whereas there are many examples of systems where standard methods really fail and have a great deal of difficulty. And we've had some examples of that through the week. So systems with d-states or where van der Waals interactions are important, for example. You know, this is a clear place where one can do a quantum Monte Carlo calculation. Where many different oxidation states are present in either one material at the same time or between different phases. This is an area which is quite difficult right now. In more mean field methods, obviously where the DFT band gap is badly wrong, that tends to indicate that hybridizations are off in the material, and so that can also be a source of inaccuracy. And similarly for molecular systems and chemistry, if there's a lot of multi-reference character, then coupled cluster techniques even will have a great deal of difficulty. And so that's an area where a few multi-determinants in the wave function can really yield quite a good trial wave function, and the fixed mode diffusion Monte Carlo can do very well. So it's very easy for us to do multi-reference systems by comparison to some other methods. Okay, point 4. So we want to favor well-controlled and easily reproduced studies, and so we can go after mechanisms over studies treating the full materials complexity. And I expected to get some questions when I pointed this, because this may be a little bit contentious. But if we can go after a mechanism, then we're quite likely to have more robust and certainly less ambiguous results. It should be more easily reproduced by others. And so this means we can perhaps get out of treating full materials complexity. And so, for example, if we can perhaps simplify geometry, if we're certain this doesn't change the fundamental interactions in the system, this is going to make our life easier, and it's going to be easier for someone else to reproduce these calculations either with QMC or some other method. Similarly, we could look at generic features of parent compounds other than the full complex system. So, for example, if we're looking at fuel cell materials, these are transition metal oxides with quite a lot of dopants in, if we use the ones that are used industrially. Well, we could perhaps understand a great deal about the system by looking at the parent materials, much simpler oxides, and still have very useful, valid scientific work. Of course, the corollary to all of this is that it is good to eventually reach full complexity and full accuracy in these materials. So maybe one would want to do a 1-2 sort of study. So number 5, how can we leverage, think about leveraging cheaper methods to minimize the number of QMC calculations required. So one strategy that one can follow is using quantum Monte Carlo to validate a particular choice of an easier to apply or a cheaper method. This could be DFT, this could be Hartree-Fock, this could be even a model Hamiltonian. And then what we could do is think about building a correction scheme when we understand the failings of this particular cheaper method. And this is quite significant because we really want to inform other theorists, perhaps other experimentalists, material scientists, chemists, and so on. And so, of course, we can't necessarily expect everyone to do a full quantum Monte Carlo calculation for those materials. And if we have some correction scheme or a cheaper model, then that can be used by others. So that's going to be much more interesting. This, of course, implies that we understand the physics and chemistry of what's going on in this material. So those were some more sort of philosophical points. Point number 6 is really very direct, right? This is one we've heard a few times. So test pseudopotentials early. So we've had a variety of questions on pseudopotentials, and it's still the case that you could be the first person to run an element, at least certainly in a material or a molecule, anything beyond an atom in quantum Monte Carlo.
Successfully.
Oh, successfully, right? So, of course, you know, the periodic table is arranged according to chemical trends, right? That's the whole point of the periodic table. So if someone has done an element, you know, to the side or one in a column above, one expects to have reasonable success. But nevertheless, there can be surprises, and you want to catch these as early in your study as possible. And I should point out this has happened to me relatively recently. And so the risk here is that if you change the pseudopotential at some stage, you're going to have to recompute absolutely everything. And so that can be quite costly, not only of computer time, but also of your time. Now, of course, the project suite makes this a lot easier. That's a great advantage. But nevertheless, it's important to build in some simple checks early in the investigation. So check the dimer's okay, check the excitations of the atom are okay. Sanity check that if you're doing a solid state calculation, perhaps that the lattice constants are okay. If the variational Monte Carlo is a long way off, then there's a little hint there that you're going to have to look a little bit more carefully. And just to build on this, just to continue on this point, so when planning an investigation, you of course want to build in an early check of your calculations. So for example, clearly one wants to, from early runs, you want to work out the required statistics and cost. And of course, if they don't look affordable, one of the nice advantages of quantum Monte Carlo is that we know the computers are going to get better. And so you may just be able to postpone this a few years and come back to it. So I have a few projects that I have set up before, and I do the variational Monte Carlo calculation, and if they seem just to be a little bit too noisy, then actually I can work out when I'm going to be able to do them, even if the methods don't improve at all. And of course what happens is that not only do the computers get better, but the methods get somewhat better. So we have slightly better trial wave functions, and we can just come back to them. Another example of this is, instead of doing full diffusion Monte Carlo for solid state calculation, have a look at what the finite size errors are in variational Monte Carlo. Because if they're already very difficult in variational Monte Carlo, then it's going to be very hard to do the diffusion Monte Carlo runs. And similarly, if one's doing the easy case really is if you have a large set of molecules, then obviously you want to do the full analysis of whatever properties you're interested in one or a few before doing the whole set. So of course there's a lot of talk about expense, and we're going to have a talk about computational resources following this one. But we have to be careful. A study does not have to be expensive to be worthwhile. There's a lot of interesting physics and chemistry that can be done in small systems. And particularly when starting out, it's worth bearing in mind that most QMC studies really are going to be new and are going to be publishable. So one can pick something that's a little less costly initially. And of course, just because something is expensive and is done on a larger supercomputer does not mean it's correct. Actually, an example of this, I noticed that Trular in JCTC had a paper looking at the vanadium dimer very recently in density functional theory. And the predictions there are basically all over the place by many, many kilocalories. And this is analyzed and understood in terms of level alignment varying between different DFTs. And it seems to me very likely that there are other related systems where similar effects might be going on, and that could be an area where one used quantum Monte Carlo. We would certainly like to get the right answer in those cases. So number 9, a little bit more practical. Obviously, you want to think about what the likely degree of error cancellation might be when doing different runs. So of course, error cancellation is most favored when comparing similar systems. So for example, if we're looking at binding of two graphene planes, as was touched upon earlier, right? Then we're only comparing systems containing carbon, and so pseudopotential errors are quite likely, we don't know that for sure, to cancel. Now, of course, for carbon, we don't have really many worries about the pseudopotential, but this would also carry through to one of the layered chalcogenides, for example. And so just generally, this issue of error cancellation highlights, I think, the importance of these well-controlled benchmark studies that, for example, Luke showed us earlier in the week, because these studies intentionally include different species, different bonds, and so on, and so highlight these kind of errors where there may be non-cancellation. Similarly, we want to think about the finite size error when assessing the difficulty. And of course, we can already get a clue what this might be, because it's never going to be any better than what it is in density functional theory or in quantum chemistry for the same system. So for example, if we're looking at a vacancy in a solid or some defect, then we have relaxation of the structure going out, and we're going to need a certain minimum size in order to recover essentially the elastic energy or the deformation introduced by that defect. And so that's never going to be small in quantum Monte Carlo. Smaller in quantum Monte Carlo. So if the DFT calculation requires 500 atoms to get the level of accuracy that one needs to make progress in the understanding of that defect, then the QMC calculation is going to need to be at least 500 atoms. And of course, because of the real space Coulomb interaction and the correlations, it's likely to be a little bit larger. So this is something we can think about in our planning.
There actually are some you can always send a counterexample.
Exactly. Yes, I'm glad for speaking up. Yeah. So what's an example where the effects are smaller?
Well, it's when the DFT or the quantum chemistry is pathological, and the electron gas is a pure case. We were able to easily do this with QMC 30 years ago, but no one can tell us what the Hartrud-Fock solution is for the electron gas.
Yeah.
Because it involves probably 10 to the 10th electrons you would need because of symmetry breaking,
Yeah.
which is completely pathological.
Right. So David has a good point. So there are pathological cases, and for sure there's a few. If we think a little bit further, I'm sure we can come up with some more exceptions to this. But I think it's pretty rare that life is going to be easier.
Just understand what's
Yeah,
going
exactly.
on.
Right. Similarly, a related point, we need to think about what the statistical properties of the properties of interest are. We've had a lot of discussion about energies and thermodynamics in this training. So of course, I'm going to make a point here about the scaling of the statistics. So of course, for studies are normally going to be much easier, for example, than defect studies. And that's because for a bulk study, we'll be reporting the cohesive energy, for example, which is reported per primitive cell, right? So it's like a concentration, right? It's a number that shouldn't change with the size of our supercell, other than for finite size error. So as we take progressively larger supercells in our finite size work, we are, of course, including more primitive cells in the calculation, and so we get better statistics. Whereas if we have a defect calculation or absorption energy with just one molecule, then we only ever have one of those interactions in the system, independent of the system size. So in that case, the bulk study is going to be a factor n better, or n might be the number of primitive cells, than the defect study. So this is why defect studies are much harder or much more costly than bulk studies. We want to consider many body properties. So we've had a lot of focus on energetics, which many other theories can get to, of course, but we shouldn't forget that quantum Monte Carlo is a full many body method, and in most cases we have the full wave function available, or we can get to it. And so this means that we can look at correlation functions and many body properties that you just can't get to with a mean field theory. Right? For example, the density matrix in a density functional theory, a single particle theory, is very boring, right? It's a non-interacting theory, so it's 1 and then it goes down to 0. Exactly. Whereas in a fully interacting picture, this is going to be smeared out, Fermi-like, and we can learn something about the system there. So that's a way of getting at a property that you don't have to worry about some density functional person coming along and commenting on directly. And more to the point, of course, there may be some insight into the physical system. Okay, so I got through that without too many objections. So now I want to give some examples to point out what makes a study easier or harder. And I'm going to do this from papers that collaborators here have worked on to avoid too much controversy. And so I'm going to assign some ratings for these studies. So my sister's a weather forecaster. I think this is legitimate. So we have a sunny outlook, a few worries with some clouds, and then since we're in Chicago and we have a tornado warning and safety discussions earlier, so we're going to have large risks indicated by a tornado. And so that's something, not to say we shouldn't do the study, but we should understand that there's going to be more things we have to look at there. So it's quite completely okay to do something that's risky, maybe a big breakthrough there, but I think it's good to know what one's facing. So first I'm going to pick on Miguel's study benchmarking the accuracy of quantum Monte Carlo for molecules. So in this paper, multi-determinantal wave functions were applied both to atoms and for a range of molecules. Right, so we have correlation energy for a range of atoms, and a study to show that higher correlation energy, greater accuracy, was achieved when we worked harder on the wave function. And then we went on to look at the full test set, how the diffusion Monte Carlo energy would improve as one takes progressively more sophisticated wave functions, and also how the VMC error would similarly decrease with improved wave functions, and obviously one goes on to compare this with how the quantum chemical methods are going. So what might be the risks associated with this study? First of all, of course, what's the audience? So this is a benchmarking study. We're attempting to demonstrate how well the method works or can be made to work. So we'd hope or expect that the wider electronic structure and quantum chemistry community would be interested in this work. And a major advantage of doing this kind of study is that, of course, you can just do one molecule. Right? If something goes horribly wrong in one molecule and you learn that you have to work much harder on the trial wave function than you expected, or there's some pseudopotential difficulty, for example, then obviously you can stop at that point. And we haven't invested too much, right? So the project will go down a different axis. Similarly, individual molecular calculations can be quite cheap. And generally, we obviously wish to demonstrate that high accuracy can be obtained if we work hard enough. This is a core tenet of the method. But as a sort of a disadvantage, of course, there are already other methods that can solve these sets of molecules accurately and quickly. So this is sort of a forward-looking study, or we want to be doing larger molecules in future. Nevertheless, not too many risks doing this kind of work. So then what about the solid state case? So this is Luke Schulenberger's calculations. We're looking at the accuracy of quantum Monte Carlo for solids. And this paper is actually, it's not about energetics, it's not about thermodynamics. It's about how well structural properties are reproduced, such as the volume and bulk moduli. So this is done for a range of ionic, metallic, covalent, and van der Waals solids. And this is all done with standard Slater-Jastrow wave functions. This is very similar to the molecular cases. Similar for audience. It's mostly a theoretical audience, I'd suggest. Similarly, we can stop after one solid if there's some problems. So for example, we don't necessarily have to pick the most easy one to do first. We might even want to pick the hardest one that we're considering to do first, because when we know we've done that, we can sleep relatively easily and know that the others are going to work. Of course, the slight downside for this study compared with the previous one is that solids are more expensive than molecules. Right? To do solids accurately, we have to carefully extrapolate not only the time step, but also very carefully converge the finite size errors. So we're going to have to do progressively larger and larger supercells, and that can be costly. Yes?
You are essentially talking about the energy, just the energy calculations here, right? I mean, there are a lot of other properties of solids.
So the question was, I'm essentially talking about the energies here. There's lots of other properties of solids. Well, actually, I'm not talking about the energies. In this paper, it's talking about, this graph is for volumes, and there's a similar graph for the bulk modulus.
Those are still energetic.
Yes, oh yes, and so on. But nevertheless, it's showing convergence or seeing how that property fares for a quantity other than the energy. And we have to be very careful when we look at novel properties to make sure that they're well converged. So these are obviously intimately related, but this paper is about structural features.
Yeah, the reason I'm saying that is, if you even within solids, I can think of a hierarchy of things which are a little bit more difficult.
Exactly. So the comment was that even in solids, we can think of a hierarchy of properties that are even more difficult. Agreed, right? So one would start with this, and then we could go on to look at phonons, for example, right? We can do progressively higher derivatives of properties related to the energy, essentially.
Or even as we spoke yesterday, band gap.
Exactly, yes. So this is finally submitted or resubmitted. So this is a study of graphite binding, and I'm showing results for AA stacked graphite. Remember that graphite is normally AB stacked, so the planes of carbon alternate. In this study, they're all lined up in AA stacking, and then we've also put lithium into the system because, of course, that's the anode used in essentially all lithium-ion batteries. So what's shown here is the binding energy against lattice spacing, and the QMC points are here. So here are QMC points with very small error bars. And experiment, it's going to be very hard to see at the back, maybe even at the front. There's actually a few people who've grown epilayers of AA stacked graphite, 3.55 angstrom, and you see we're within 0.1 angstrom. This is the standard Slater-Jastrow wave function. And to make a connection to the previous question, we didn't have to really specially target the optimization in this case. And one thing that's going to be very hard to see, but actually the speaker last night, Julia Gali, along with Leonardo Spano a few years ago, did AB stacked graphite, and that actually runs along through here. And so the error bars are very hard to see, but they're somewhat larger. But nevertheless, if AB graphite is here, then we see that AA is appropriately up here, so higher in energy and slightly larger lattice constant, as would be expected. So what are the issues and what are the audience here? So of course, one can consider this to be a van der Waals benchmark, so this affects the electronic structure community. But of course, the lithium-ion battery modeling community hopefully be interested in this work because we need accurate methods to look at lithium in anodes and cathodes of battery materials. And there are certainly some errors floating around in the DFT of a few tenths of a volt when compared with experimental voltages. So this is a well-identified problem. When we started this, of course, we knew that Julia and co-workers had run AB graphite with really nice results. There's a PRL I can give you the reference on a few years ago. So it seemed extremely likely that the AA study would work without any problems whatsoever, right? It's basically the same system. It's more or less the same supercell. We can use the same quality of trial wave function, so this is really very straightforward. And clearly we have previous good results for carbon vacancy, for the carbon diamond and the carbon vacancy in the literature. The only real difficulty, I would say, of doing this work relates to cost. Now, I didn't show these results, but we put a single lithium atom into the supercell and then looked at the binding energy of that. And so that's a much more costly calculation than just looking at the binding of carbon sheets, because we only ever have one lithium atom. So while the graphite binding might take some hundreds of thousands of hours to run with that sort of accuracy, by the time one does the full study with lithium binding in this work, then one can get into the millions of hours.
Or is the size effect? Because once you put a defect or something in, there are correlations.
So the question was, is this a size effect because of correlations?
Right.
I'd say not really. It's essentially because we only have one lithium atom, which will.
Is it 10x more expensive?
Right. So these quantities are going to be reported either per lithium atom or per primitive cell of the graphite. And so the reason it's much more expensive is that when we do the graphite binding, we are reporting the binding per carbon atom, and as we take progressively larger supercells, we add more carbon atoms. Right. So yes, we're having to pay for larger cells, but we're also gaining more carbon atoms that are going to normalize the energy that we're reporting. Whereas if we only have one lithium and we take larger and larger cells, we don't gain any additional lithium to divide through by. So this is the same as with a defect or a binding energy of a molecule on a surface.
Of course, asymptotically, there are much better methods that you could add the defect as like a thermodynamic integration to, instead of doing two calculations and subtracting, right?
So there may be tricks to reduce the cost. There are always tricks, right? So the point here is if you have one of these things, you might want to think about, is there a trick that I could be using to make my life easier?
Right. So the other reason I was asking that was, is this comparative expense of 10x, is that more of the methodology problem, limited by the methodology of QMC? I tend to think that it is how you estimate that probably led to 10x more than the QMC intrinsic limit.
Yeah, it's got to be. I mean, classically, you wouldn't do it this way.
No.
It's because QMC has got stuck in a certain way of doing things.
Right. So clearly there should be better ways of getting these energies than just subtract. So what we're essentially doing when we do a defect binding is we take a very big number and another very big number that's nearly the same, and we subtract them. And as we do larger and larger systems, of course, the numbers are getting bigger, but what we're trying to resolve does not, right? So clearly there should be a way of decomposing the energy, for example, which would reduce the cost here and get greater error cancellation as well. Let me give another example. So this is we've had some questions about studies of defects in semiconductors or in solids. Right? So there's a lot of question and uncertainty there, not only coming from electronic structure methods, but also because these are very hard to measure experimentally. So if we have high accuracy theory, we have a good chance to have some impact outside the electronic structure community. So this is a paper on the archive looking at a vacancy in zinc oxide, which is quite a famous defect. There's been a lot of work done on it. And so what was done within the quantum Monte Carlo is not just to look at the single neutral vacancy, but also the charged vacancy, and then to follow through with the defect thermodynamic formalism of Chris van der Waal and Neugebauer and so on, and then make comparisons to how the DFT is performing. I'm going to skip over some of the physics here. But so, for example, one thing that was interesting was that so this shows the Fermi level against the formation energy of the carbon vacancy. The diffusion Monte Carlo actually shows a different behavior. We see there's actually positive U behavior here compared to what one of the best theoretical predictions, which uses a tuned hybrid DFT functional, actually gives. So there's some slight difference in the physics in this system. And obviously one can then go on and apply this to other defects in the system. So what are the issues with this kind of work? So obviously there's a lot of interest in zinc oxide. If one looks at the number of papers on zinc oxide, it's really very large. In terms of favoring looking at this material in quantum Monte Carlo, we know that although the band gap is relatively poor in DFT, overall the electronic structure is we could say reasonably okay. That is, the system is not metallic, for example. So the ground state from DFT that we're feeding into our to use trial wave functions in quantum Monte Carlo may be a reasonable starting point. We're going to have to test, but obviously it could be worse. It's obviously a little bit harder than just looking at silicon or carbon, because obviously zinc's starting to get heavy. One thing that took a lot of work in this study was carefully developing a zinc potential. And so one could consider this either a strength or weakness, but this was certainly an extra source of effort in the investigation, carefully testing that zinc potential, because very little had been done with zinc before. Of course, this is a solid state calculation. We have to have large supercells. And so one little risk here is that we're not going to know the quality of the results until large cells have been run. So there can be a lot of upfront expense in these kinds of studies, right? As we go to larger and larger cells, the levels may shift quite a way due to finite size effects, right? Some defects are worse than others. So just because we can do the vacancy in zinc oxide does not mean that every vacancy in a semiconductor is durable. Some may be easier, some may be hard, some may be much harder. And I'd also highlight, I think the main difficulty in this work actually is the finite size errors that I just mentioned. And because we're using these real space wave functions that we were using yesterday in the labs, which use a lot of memory, what actually stops us presently in terms of how far we can go is the memory usage on the node. So as we do larger and larger cells with low symmetry, a lot of memory is being spent. And Luke gave examples of some alternative schemes that we're looking at, which will reduce that memory requirement and let us go to larger cells. So this would also be a concern with any other study with low symmetry where we need to do large supercells. Let me now discuss this calculation on the cuprate. So this is calcium copper oxide. This just published paper, and this is look at the exchange coupling in the material. And I mentioned Lucas Wagner has also done some very similar calculations looking at more properties on lanthanum copper oxide. Very interesting study. That's on the archive. So what are the issues with looking at calcium copper oxide, which is of course a 1D cuprate of the high temperatures for the 2D high temperature superconductors? So of course we know the audience is potentially quite large, right? We know that the electronic structure of cuprates is very important. Of course, the experimentalists have already measured the exchange constants in these materials, but nevertheless this is feeding into the models that are used, And we'd certainly like to be able to predict this for a series of cuprates without any empirical fitting. But a certain risk when doing this study, certainly by comparison to the zinc oxide, is that we know that the underlying DFT ground state is wrong. So these systems are metallic if you just do LDA. So there's no band gap when there should be one. And so this immediately tells us that the density is going to be somewhat wrong, and the orbitals in the trial wave function may just be much less good. Of course, this can be fixed, quote unquote, by use of DFT plus U or hybrid functionals. That's quite common. But nevertheless, we know we're going to have to test different trial wave functions. And that's what was done in the study, testing different trial wave functions variationally within diffusion Monte Carlo to find the best ones. Right? This was less essential in the previous studies, although of course that's also a nice thing to do. We had to carefully develop a copper potential here and test that very carefully. If there's an error in there, it could very easily affect the exchange constant. As a slight plus, as we move to larger cells in a finite size study, we of course sample more spins. So this can give improved statistics. But nevertheless, I think we always have to live with this in these Monte Carlo calculations. You're not going to know the quality of the results until you've done the larger calculations and done all the finite size studies, because we're seeking a sharp comparison with experiment. So this is something I'd say is a bit more risky than the previous work, pretty much because of these issues with the DFT ground state and having to do much more testing. Of course, because we have a variational method, one can test different trial wave functions, and if one gets a lower energy, then we know that we have a better solution, and more than likely, other properties will come out much better. So I hope I've given a slightly different flavor in this talk from the previous talks we've had in this training. It's important to consider the overall complexities and think about what the risks might be in these quantum Monte Carlo investigations, because they're really somewhat different from more established electronic structure methods, such as density functional theory or quantum chemistry. So one wants to think through the statistics, for example, and how the statistical properties of the property of interest may vary depending on how you set up the calculation, for example. And so I would sort of summarize also by saying, well, that then small molecules and bulk properties are obviously more attractive for an initial QMC project because they have less of these risks. But obviously how much risk one takes is an individual choice, and that's up to you.